Questions on the homework assignment before we get started. De Morvay's theorem. This theorem is very useful because it's going to help us solve complex numbers or complex solutions. So De Morvay's theorem, if z equals r cosine of theta plus I sine of theta. So if this is a complex number and n is a positive integer, then z to the n is equal to r cosine of theta plus I sine of theta. Or r to the n is equal to cosine of n theta plus I sine of n theta. Sorry, I got ahead of myself. This helps us show any power. Thus, if we look at something like this here, we're trying to find -1 plus the square root of 3, I to the 12th. We can use this theorem here. Now the other way, because it is possible to not use this theorem, well, we can multiply it by itself 12 times, which isn't preferable. The other option is to use our factoring tree. Well, to get there, because there's squared, cubed, fourth, fifth, sixth, seventh, eighth. Well, I already committed to this. We're going. 4, 84, 6, 126. 6, 7, 8, 9. Oh, well, that's helpful. Zero. And I'm going to stop there because we have 2 more rows, but these are the coefficients of the numbers in front of it. Now, our radicals and i's will simplify things down and make it a little bit easier to work with, but we have a lot of expressions and a lot of terms. And the biggest one, because I can tell you that if we multiplied it out, is going to end up being -1 to the 12th plus, and our last term is going to be the square root of 3i to the 12th. And there's going to be a lot of other terms that simplify and cancel each other out in the middle, but it's a lot more work than it's worth. So the first thing we need to do is get this here, our -1 plus 3 square root of 3i, into this form. So we need to find the value of r, which is the square root of a squared plus b squared, and theta, which is equal to tangent inverse of b over a. R in our case is going to be the square root of -1 squared plus square root of 3 squared. Thought that had loaded already, but apparently not. Second square root, -1 squared plus square root of 3 squared gives us 2. So the value of r in our case is 2. Theta is equal to tangent inverse of b over a I have no idea why I wrote 2. It should be negative 1. So negative square root of 3. So we can say second tangent inverse square root of 3 over negative 1. That'll tell us it is negative 60 degrees. Okay. Now for most of these here, we would prefer theta to be between 0 and 2 pi, or 0 and 360. So if we look at the graph to kind of see where this point should be, well, in the complex plane, they gave us the point negative 1, positive square root of 3. So our point is up here. The point we found from our tangent inverse, negative 60 degrees, is down in the fourth. We need it in the second. So interestingly enough, we can add 180 degrees to it. Or if this had been in radians, we would add pi. And if we do this here, our actual angle that we're looking for is 120 degrees. And if we want to check that, we can take tangent of 120 and see that we get negative square root of 3. So that is the correct angle. Thus, making the number or kind of equation we want as z is equal to 2 cosine of 120 plus I sine of 120. Questions on this here, how we got this started out? Now what we're wanting to do is take this to the 12th power. So I'm going to scroll down. So we're saying z to the 12th, which for us is, I'll write the general form again over here. Z to the nth is equal to r to the nth cosine of n theta plus I sine of n theta. Here n is 12. Our r is 2, so we have 2 to the 12th. Cosine of, well again, n is 12. And we're multiplying it by 120 plus I sine of 12 times 120. Questions on this here? Question on anything we've done so far? Well, we all know 2 to the 12th. We know what that is. 4056. I don't know. 4096. And I was just making a guess. I had no clue. Now at this point here, we simplify what's inside our parentheses. So 12 times 120. Well, 12 times 12 is 'so if we multiply 12 by 120, we just need to add a 0. So 1,440 plus I sine of 1,440. And that's it there. Now, if we want to actually see what multiplying 1 minus the square root of 3i by itself 12 times would end up being, all we got to do is multiply these two here. So our 4096 by cosine of 1440 is 4096. Come on. We can do the same thing with sine of 1440, which is plus 0 I. Thus, the answer is 4096. Which is, for lack of a better term, kind of infuriating that -1 plus the square root of 3i to the 12th. Multiplying that by itself 12 times is a single number. And knowing that, well, apparently the graphing calculator was not awake yet. Parentheses, -1 plus square root of 3i to the 12th. That's it. Now, it seems like we could have done that originally. Why did we take this time to do it the other way? Just changing the one number from 12 to 13 gives us this kind of decimal here. Now, we could go about trying to figure out how we get to it. And, well, I'm going to add 4096 to it just to get rid of the front number and look at this here. Now, we know both numbers have 4096 in common. So whatever this number is, the radical should be something times 4096. I divide it out, we get this here. I'm going to take a stab in the dark and say square root of 3. Okay, so what it tells us to the 13th power is, well, this is negative 4096. Look back at it. Plus, okay, thing, 4096 I square roots of 3. So we could still do these in the calculator, but I have to know how to dismantle them, then know what the approximation of the square root of 3, or pick the right radical to go from there. So this theorem does take a lot of the guesswork out and makes it a little bit easier to work. Questions on this here? Now, this here is the other one that's kind of cool. We can find, for a positive integer n, complex number, z equals r cosine theta plus I sine theta, has exactly n distinct nth roots given by this equation here. Normally we deal with it in 2 pi. We can technically deal with it in, or this is radians. I don't know why I was about to say radians. We could deal with it or use it in degrees. Z sub k is equal to the nth root of r cosine of theta plus 360k over n plus I sine of theta plus 360k over n. Make sure I write my Greek letters correctly. We can do the same thing and the same type of operation. Now this feels like it should be very, very complicated because every math instinct that we have been taught intentionally or unintentionally, something about mathematics tells us that things always have to be harder than they actually appear or what they might seem, because there's no way it can be easy. Once you see how this has worked and how this is done, I like these because they work kind of nice, very systematic once we get them set up, and they follow a very distinct pattern. Because for this here, one, we do have to get whatever we're working with into this form, no matter what it is. Then we need to find our nth root of r and have our theta and n plugged in here. And the k is always going to be 1 less than whatever n is. So if n is 3, it's going to be 0, 1, 2. If it's 4, it's 0, 1, 2, 3. If n is 2, it's 0 and 1. So we have this here. So first one we're going to work with is to find the square root of 5i. Square root. N is 2. Square root 2. Which means k is 1 less than n. So the values of k are 0 and 1. Now the only other two things we need this formula are r and theta. Well, r is equal to the square root of a squared plus b squared. I know b. B is the number in front of I, because our a plus bi. What's our a value? Is there a number in a's place? Well, no, because there's not a number written in front of 5i. 0. Yeah. If it's not written and there's a variable there, it's understood to be 1. But if it's not there at all, it's completely gone at 0. So the first thing we need to do is calculate this here. Now there's no real reason for me to put 0 squared, because it doesn't add anything to this. So we're really looking at the square root of 5 squared, which is 5. The other thing we're missing is theta. Theta is equal to tangent inverse of b over a, yes? Can we even plug this into the calculator? No, because we can't divide by 0, correct? But this still has a value. And to find that value, I've really got to look at the chart. Because what we're saying is our a, bi. Well, a is 0, so I'm not going left or right, but we're going up 5 to our point. So our 5i is the point straight up. Well, we can do this first one in radians, which actually tells us our angle's pi over 2, 90 degrees. So if we get this division of 0 because a is 0, our angle is going to be one of two things. It's either going to be pi over 2 or straight down at 3 pi over 2, either 90 degrees or 270. Are the main two that we're going to look at. We're not going to consider any of their coterminal angles, because we could do 90 plus 360 is 450. 450 and 90 would give us the same value. We're just looking at 0 to 360. Or 0 to pi or 2 pi. Questions on this here? So, I'm going to get this color here. As our general form says z z sub k, our roots, is equal to the nth root of r times cosine of theta plus 2 pi k over n plus I sine of theta plus 2 pi k over n. This is the general form. Now with the square root, we're going to have two solutions. We're going to have two values. And the way we do this is we start off with the first value of k, which is 0, equals and we're going to fill the information in as we go. Now in our case is 2, square root. Now we don't necessarily have to write a 2 in for square roots, because if we just have a radical, it's understood to be 2. Our R value is 5. And really that's the last time 5 shows up for this step here. 5 is only going to be inside that radical outside. Inside the parentheses is cosine of our angle that we found is pi over 2 plus 2 pi times our k value, which in this case is 0. Divided by n, well, n in our case is 2 plus I sine. Well, we're going to have the exact same thing. Pi over 2 plus 2 pi times 0 over k. You're ready to simplify this down. So our z sub 0. Well, square root of 5 is just square root of 5. Yeah. We can turn it into a decimal, but we can leave it here also. Cosine of, well, I'm going to type that entire thing into the calculator just as it is. 30xs fraction pi over 2 plus 2 pi times 0 over 2. Now it might seem weird I'm actually typing in the 2 pi times 0, because 2 pi times 0 is 0, just leaving us with pi over 2 divided by 2, which is pi over 4. So it tells us we have cosine of pi over 4 plus I sine of pi over 4. Now at this point here, we can take this a step further to find the solutions for this here. So we can distribute. We can multiply our square root of 5 and cosine of pi over 4. In the calculator, I will have to change this to radians. Second square root of 5 cosine of pi over 4 is square root 10 over 2. Okay. Plus. We'll do the same thing with sine. Second square root 5 sine of pi over 4. Square root 10 over 2. So plus square root 10 over 2 I. Then we'll go with purple. Questions on how we got the first one? All right. We finished with z sub 0. Now we're going to go to z sub 1. So all that's changed as well. Square root of 5 is still the same. Parentheses. Cosine of pi over 2 plus 2 pi times, well, our k value is now 1 instead of 0. We changed it from 0 to 1. Plus I sine of pi over 2 plus 2 pi times 1 over 2. And just like before, we're going to type what's inside cosine into the calculator. Well, what's inside cosine and sine. Fraction pi over 2 plus 2 pi times 1 over 2 is pi over 4. And lastly, we can multiply this out. So we'd have second square root of 5 cosine of 5 pi over 4 is negative square root 10 over 2. And I have a feeling 5 sine 5 pi over 4 is also negative minus square root 10 over 2 I. Is our final answer. Questions on this here? Now we said this is the final answer, and we can kind of somewhat demonstrate that. Because we said is what we were trying to find is the square root of 5, and he gave us these two answers. So really what we're saying, whenever we take the square root, is what times or what two things multiply together to give us 5i. That's what we're trying to find. And what should happen, I've done this before, is if we distribute this back out, we should get back to the square, or 5i. Now our square root 10 over 2 times negative square root 10 over 2, we'd have negative. Our 2 times 2 would be 4. Square root of 10 times square root of 10 is the square root of 10 squared, which is just 10. So we have negative 4 tenths, and we can reduce that in a minute. And our 10 squared root of 2 times negative 10 squared root of 2 over 2i is going to be minus 10 over 4i. 10 square root of 10 over 2i times negative is going to give us the same thing. And lastly, positive square root of 10 over 2i times negative square root of 10 over 2i is going to be negative 10 over 4i squared. And as we've seen already, I squared is negative 1, which is going to change that from a negative to positive 10 fourths. Negative 10 fourths plus positive 10 fourths is 0. We do have our like term in the middle. Negative 10 fourths I minus 10 fourths I. Negative 10 minus 10 is negative 20 over 4i. 20 is indeed divisible by 4, giving us negative 5i. Well, almost got us there. I'd have to look into why. There's a, I'll go backwards. So I'm looking at over 4 over 2. Okay. Yeah. That is odd. But those are our two solutions for the square root of 5i. Should be. Yep. Yeah, because our pi over 4 did give us positive. Yep. Oh, 32. Trying to figure out where in the heck I got that from. Homework. are the correct answers. I don't know exactly why it gave us a negative instead of the positive version of the answer. But I do find that interesting. I think it's something to do with it being squared. But there you have it. Because those are indeed the correct solutions. Questions on this here? Questions on anything we've done so far? Yeah. Because they don't even talk about multiplying it or doing that. That's why I've never done it before. I do find that interesting. Yeah. Because, I mean, it's the 3 pi over 2. So it might have something in common with that. That's my best guess. We're going to do one more today, and then we'll finish up the note sheet too on Monday. So we want to find the square root of 2 plus 2i. So square root 2. So our n value is 2. Our k value, just like the last one, would be 0 and 1. The only thing we're missing is r and theta. Now, we didn't turn the last one into a complex r times cosine of theta plus I sine of theta because we really just needed these values. Now, the first thing we need to do is find the value of r. R is our a squared plus b squared. And for us, that'd be the square root of 2 squared plus 2 squared. Well, our square root of 2 squared plus 2 squared is not going to be as, well, 2 squared is 4, 2 squared is 4, so r is the square root of 8. Now, as you're looking at this here, you might be saying, well, we can actually simplify the square root of 8. It's actually going to be better to leave it alone because when we start doing the formula, we have to take the square, a certain root of r. And if we have r as what it actually simplifies down to, 2 square roots of 2, we have to then take whatever root that is, and it becomes a little bit more challenging. Theta is tangent inverse of b over a. So for us, we're taking tangent inverse of 2 over 2. The calculator. One more time. One more. Tangent inverse of 2 over 2 is this decimal, or pi over 4. Questions on how we found this here? Now we've seen how the formula works. Because our z sub 0 is equal to the nth root, so square root of r. So the square root of the square root of 8 times cosine of theta, which is pi over 4 in our case, plus 2 pi times k over n, plus I sine of pi over 4 plus 2 pi times our k value, which is 0 for now, over n. So we get all this here. Now, one of the first things we do need to simplify is the square root of the square root of 8. Now, to get this and really see what this is, we're really going to need to go back to our properties of radicals. The nth root of a to the x is the same as a to the x over n. So what this is telling us is that our square root on the outside is really putting our square root of 8 to the 1/2 power. Well, the square root of 8 is also 8 to the 1/2. So we'll fill in the other side in a minute, but really what we have here is 8 to the 1/4, which is the 4th root of 8. Now we could check that if we want, because I can grab the calculator, say 4, our nth root, 8 is this number here. Now what we were trying to see if this is the same as the square root of the square root of 8. We get the same value. If we want to doubly make sure, we can subtract the two from each other, and it does give us 0. Some may argue that that's not a surefire way because there are some approximations that the calculator will approximate as 0, but aren't 0, but here they are the same. Well, we do need to finish the rest of this. Because here we have cosine of pi over 4 plus 2 pi times 0 over 2 over 4 plus 2 pi times 0 over 2 pi over 8. Well, it took us a little less time to get there than it did the other one. Questions on how we got to this here? All right. Now, before we move on to actually multiplying this out, I want to go on and find these of 1, our other one. And for this one here, I'm going to write them next to each other. Normally, we would just keep going down the page. But since we only have one more, we do have room. Now, the first part, like the original one, we have the square root of the square root of 8. But what is the square root of the square root of 8? Well, we already found it. It's the 4th root of 8. Yes? So we don't have to rewrite it as the square root of the square root of 8 anymore, because we know it's the 4th root of 8. Cosine. Well, this is our pi over 4 plus I, back up, pi over 4 plus 2 pi times our k value, which is now 1, plus I sine of pi over 4 plus 2 pi times 1 over 2. Now we just need to figure out what our pi over 4 plus 2 pi times 1 over 2 is. So we can grab the calculator again. Well, this is kind of nice because the last thing we typed in was this here, yes? I can now just replace the 0 with 1. 9 pi over 8. Now, if we want to see what this looks like multiplied together, 4th root of 8, cosine of, let's look at z of 0 first, pi over 8. Wrong calculator. Pi over 8 is this here. We can't convert it to a decimal or to a fraction. It is just a decimal, 1.55377. We'll go out for 1.5538. We'll do the same thing with sine. 4th root of 8 sine of pi over 8, 0.6436. Make sure I'm getting this right. 356. Or not 356. 36. All right. So there's one of our solutions. We'll do the same thing with the other one. But this time, instead of it being pi over 8, it is 9 pi over 8. Too far. Negative 1.5538. Those decimals look similar, yes? And if I were to guess, I'd say negative 0.6436. But let's see. Yep. Thus, these are our two answers. And we'll stop there for today.